Hello everyone. So today we are going to solve another interesting problem number 261 validity. It's a premium problem on Leetcode. So I have found its substitute to solve this problem on Leetcode. It's the same problem. Here we can write our code and test out the problems algorithm that we are going to define. So what does this problem say? That we have been n nodes labeled from 0 to n and a list of undirected edges. Each edge is a pair of nodes. They want us to write a function to check whether these edges make up a valid tree. Okay, so what we have been given is we have been given five edges. We have been given five nodes. So we have been given n is equals to 5. So we have nodes ranging from 0, 1, 2, 3, 4, and we have edges directed from 0 to 1, 0 to 2, 0 to 3, and 1 to 4. So we can build a graph using these nodes and edges. So from 0 we are going to 1, from 0 we are going to 2, from 0 we are again going to 3, and from 1 we are again going to 4. So now we have to tell that whether this graph is a valid tree or not. So to do that, what we can see is we have to check for two conditions, and those two conditions are conditions when a graph is a tree. So the first condition is we need to check the connectivity. So connectivity of every node from every node to any other node, meaning we can traverse from any node to any other node. That's the first condition we need to check. And the second condition that we need to check is there are no cycles in the graph. So if we satisfy these two properties, it means that our graph is a valid tree. So which we can see we are satisfying in the current first example that we have. And how we can solve this problem? So the algorithm that I'm going to show you I'm going to show you three algorithms through which we can solve this problem. So the first algorithm is going to be BFS approach, second is going to be the DFS approach, and the third approach is going to be the union find method, union find algorithm, using which we can solve this problem. Okay, so that's how we can solve this problem. Now I'm going to write the code for all these three algorithms one by one, and the approach for all the problems, the general algorithm is going to be same. What we are going to do is first we are going to build the graph the way we build it or manually. Similarly, we will build the graph from the edges input that we have. The second step would be to apply the BFS or DFS on the graph. And the third condition, the third criteria would be to check for these two conditions, or conditions, the two conditions that we have, the connectivity and the no cycles condition in graph. Now I'm going to show you how we can model these two algorithms in the code, and we can write the solution for this. So first I'm going to discuss the first algorithm that I'm going to discuss would be the BFS approach. So this is going to be the approach one, which is BFS, right? And we are going to write the solution for this. which I'm going to show you now. So the very first thing that we need is to build graph. So we'll declare one variable g, and so I'm making the graph of index pointing to the values. So index are pointing to the neighbors. So for that I'm going to define a list of list. So for numbers, how many number of nodes that I have, that many list of list I'm going to declare. And now for every start to end in edges, we are going to build a graph. So we'll say that the start will append all the neighbors of from start we are going to where we are going to end. We'll append all those into this list that we have, and similarly we'll do for the end edges that are going to append into this. So this is one way of declaring the graph. Another way what you can also do is we can also declare it like this. So what we can do is we can also use one default dictionary of list of integers. So that would be this one. So I'm going to show you both. So this is g1. I'm going to write it as g1, this one. For now, this is for just for time. So this would be g1. So this is one graph, the one way of defining the graph. This is another way of defining the graph in g2, and I'm going to show you the result in both the cases and the only small difference in both the approaches. So here we are doing g2 dot append e and g2 of s going to append into this, and the in the edges we are going to append the start from where we are starting. So now let's print out graph g2, and we'll print out the graph g1 as well. So this is the graph 1 that I'm going to print out now, and let's run it and show you that both these graphs are same. So this is the list of list, the first one. So it wants the default dictionary. So I'm going to say that from collection import default dictionary, and since we are using BFS, so we are also going to need the DQ, so I'm also writing it. So this is the graph 1. You can see the index 0 is connected to 1, 2 and 3, and the second one is connected to 0 and 4, like we saw in the graph that we have built on our own, the same graph that we are seeing over here. Similarly, the graph 2 just output. So yeah, so this is 0, 2 is connected to 0, 3 index, third node is connected to as well 0, and fourth node is connected to 1. Similarly, in the second way, the way I declared graph 2, here the keys are the node and the connections, the another nodes, we are keeping it in the form, the neighbors basically of nodes, they are in the form of list. So you can use any of these two. I'm going to go with the first one. So I'm going to now name it back. So this is graph, this is graph, and now I'm going to, so first we have built the graph. Now we are going to apply simply our BFS. So for that we need one starting node in the queue that we are going to declare, and we one uh, set with the source that we have. And now we'll say while queue is not none, what we need to do is we need to pop out the current node. So that will use that will pop from the left of the queue, and we'll check for neighbors in the current node that we have in the graph. We want to see that if this neighbor not in the dictionary in the set that we have declared, Then we are going to process the other nodes, all the other nodes that we have. So we'll add that into the current set that we have, and we'll append those neighbor for processing into the queue. So that will do this. Why we now all we need to do is we need to apply those two conditions. Condition for connectivity, that the length of the scene mat set is equals to number of nodes. Then we'll say if it is true, then we say there is connectivity. And for no cycle condition, what we are going to say, if length of edges is not equals to n minus 1, it means the number of edges is not equals to number of nodes, then we'll immediately return false. So that's one way of writing this problem. Or we can also write it like in this way that I'm going to show you the way. So first let's run this solution, show you that this works. So now let's run it out. So it has been running perfectly, and let's submit our solution and see how it performs. So it has been accepted for all the test cases that we have over here. Okay, no worries. So this is running. Now we can also add this no cycle condition. This is the cycle condition. So if we don't want to write it like this, we can just remove this here, and we can write the no cycle condition like this. This length of scene is equals to, and this is for the connectivity, and the length of the edges equals to, basically nodes is equals to number of edges plus 1, right? So length of edges would be n minus 1. This would be the actual condition. So that has been accepted, and let's submit it. So it has been accepted for all the running cases. So this is the approach for the BFS. Now I'm going to show you how we can write this for the DFS approach. So for that, we'll keep these condition the way it is. We'll also need the graph, and the only thing that we are not going to need is the function. So we'll define our own DFS function for checking the uh, for traversing the nodes and checking whether the connectivity condition is matched. So first we need to declare one set of that we are going to visit, and we'll start our DFS function from the 0 node, and in the end we'll check for these two condition running condition that we have. All we need to do is now define a DFS function that will take one node as input, and what we'll do is, as we are getting this node that we are seeing for the very first time, we'll add to our set, and again we are going to apply the same DFS graph DFS algorithm. So we'll check that for the neighbor of the current node in the graph, if this neighbor is not in visited set, then what I'm going to do is, then simply I'm going to again recursively calls my DFS function over this neighbor. So this would be the simple approach for DFS function, DFS def for search. So now let's run this solution for all the test cases that we have. So it is, we have this quoted and visited, so that's it. So it has been accepted for this. Now let's submit for all the solutions. So it has been accepted for all the test cases that we have. So I've shown you both the approaches, how BFS and DFS could be applied over here, how to turn the BFS into DFS function, and as promised, now I'm going to show you the another method. And before moving to another method, the time complexity, I want to share the time complexity for both the approaches. The time complexity for this approach is O of n, and the space complexity is also O of n for both BFS and DFS. For both BFS and DFS approach. Now I'm going to show you another method of solving this problem as well, which is called basically the union find method. And in this method, what we'll do is, the very first thing that we are going to do is we'll traverse the edges, and if two nodes are already in the same set, what that means would be that there is a cycle. Otherwise, we will merge the two nodes into the same node, into the same set, and then decrease the number of connected components one by one, and finally check whether the number of connected components is 1 or not. So that would be the union find approach, and this is how we can write the union find approach. So I'm going to first name it. That approach is union find method that I'm going to write out. And so what is happening over here is, first what we'll do is we'll declare our parent array for each node. So that would be the list of range of all the numbers that I have, nodes that I have. And now what I'm going to do is I'm going to traverse in the edges that I have, and I'm going to find both the root of my current element that I have. So for that I'm going to write one function that will find me the root parent for both the nodes that I'm having, and I will check for the cycle. So for that I will see that this if the parent of A and the parent of B, if they both are equal, it clearly means that there is no cycle, and there is a cycle and will immediately return false in this. Otherwise we will make a union of the nodes that we have. For that we check that is this P of PA is equals to PB, and will decrement the number of counts of the component as we have seen this. And in the end, what we are going to do is we'll return the valid tree has only one component in the end. And now we need to do is to write this one function finding the root parent of any given node. So what we'll do is we'll check that if this parent node is not equals to the current node, then what we'll do is we'll do the path compression. So we'll say that is p of x is equals to find of the p of x initially. Then will if it is not and p of x is equals to find p of x, then we'll just go and return the parent of this current node that we are having. So that would be the union find approach, and let's run our solution and forms. So this has also been accepted now for all the test cases. So this has also been accepted by for all the test cases. The time complexity for this approach is basically O of n log of n, which is the time complexity for union find method, and the space complexity is O of n over here, where n are the number of nodes. So this is how you solve this problem, and I have shown the three approaches for solving this problem. So let me know guys if you have any particular problem that you want me to solve, and please like and subscribe to the channel. It helps me reaching out to you with new algorithms, and it keeps the motivation up for me, and I hope I'm helping you guys in your interview journey. Thank you. Have a nice day, and I will see you tomorrow.